Quantum mechanics is the science of the very small, the body of scientific principles that explains the behavior of matter and its interactions with energy on the scale of atoms and subatomic particles. Classical physics explains matter and energy on a scale familiar to human experience, including the behavior of astronomical bodies. It remains the key to measurement for much of modern science and technology. However, towards the end of the 19th century, scientists discovered phenomena in both the large and the small worlds that classical physics could not explain. As Thomas Kuhn explains in his analysis of the philosophy of science, the structure of scientific revolutions. Coming to terms with these limitations led to two major revolutions in physics which created a shift in the original scientific paradigm: the theory of relativity and the development of quantum mechanics. This article describes how physicists discovered the limitations of classical physics and developed the main concepts of the quantum theory that replaced it in the early decades of the 20th century. These concepts are described in roughly the order in which they were first discovered. For a more complete history of the subject, see History of Quantum Mechanics. In this sense, the word quantum means the minimum amount of any physical entity involved in an interaction. Certain characteristics of matter can take only discrete values. Light behaves in some respects like particles and in other respects like waves. Matter, particles such as electrons and atoms, exhibits wave-like behavior too. Some light sources, including neon lights, give off only certain discrete frequencies of light. Quantum mechanics shows that light, along with all other forms of electromagnetic radiation, comes in discrete units, called photons, and predicts its energies, colors, and spectral intensities. Some aspects of quantum mechanics can seem counterintuitive or even paradoxical, because they describe behavior quite different from that seen at larger length scales. In the words of Richard Feynman, quantum mechanics deals with nature as she is, absurd. For example, the uncertainty principle of quantum mechanics means that the more closely one pins down one measurement, the less precise another measurement pertaining to the same particle must become. The first quantum theory. Max Planck and blackbody radiation. Thermal radiation is electromagnetic radiation emitted from the surface of an object due to the object's internal energy. If an object is heated sufficiently, it starts to emit light at the red end of the spectrum. As it becomes red hot, heating it further causes the color to change from red to yellow, white, and blue, as light at shorter wavelengths begins to be emitted. A perfect emitter is also a perfect absorber. When it is cold, such an object looks perfectly black, because it absorbs all the light that falls on it and emits none. Consequently, an ideal thermal emitter is known as a black body, and the radiation it emits is called blackbody radiation. In the late 19th century, thermal radiation had been fairly well characterized experimentally. However, classical physics was unable to explain the relationship between temperatures and predominant frequencies of radiation. Physicists searched for a single theory that explained all the experimental results. The first model that was able to explain the full spectrum of thermal radiation was put forward by Max Planck in 1900. He proposed a mathematical model in which the thermal radiation was in equilibrium with a set of harmonic oscillators. To reproduce the experimental results, he had to assume that each oscillator produced an integer number of units of energy at its single characteristic frequency, rather than being able to emit in any arbitrary amount of energy. In other words, the energy of each oscillator was quantized. The quantum of energy for each oscillator, according to Planck, was proportional to the frequency of the oscillator. The constant of proportionality is now known as the Planck constant. The Planck constant, usually written as h, has the value of 6966629999999999996.63 times 10⁻34 Js. So, the energy E of an oscillator of frequency f is given by to change the color of such a radiating body, it is necessary to change its temperature. Planck's law explains why. Increasing the temperature of a body allows it to emit more energy overall, and means that a larger proportion of the energy is towards the violet end of the spectrum. Planck's law was the first quantum theory in physics, and Planck won the Nobel Prize in 1918, in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. At the time, however, Planck's view was that quantization was purely a mathematical construct, rather than a fundamental change in our understanding of the world. Photons. The quantization of light. In 1905, Albert Einstein took an extra step. He suggested that quantization was not just a mathematical construct, but that the energy in a beam of light actually occurs in individual packets, which are now called photons. The energy of a single photon is given by its frequency multiplied by Planck's constant. For centuries, scientists had debated between two possible theories of light. Was it a wave or did it instead comprise a stream of tiny particles? By the 19th century, the debate was generally considered to have been settled in favor of the wave theory, as it was able to explain observed effects such as refraction, diffraction, interference and polarization. James Clerk Maxwell had shown that electricity, magnetism and light are all manifestations of the same phenomenon, the electromagnetic field. Maxwell's equations, which are the complete set of laws of classical electromagnetism, describe light as waves, a combination of oscillating electric and magnetic fields. Because of the preponderance of evidence in favor of the wave theory, Einstein's ideas were met initially with great skepticism. Eventually, however, the photon model became favored. One of the most significant pieces of evidence in its favor was its ability to explain several puzzling properties of the photoelectric effect, described in the following section. Nonetheless, the wave analogy remained indispensable for helping to understand other characteristics of light: diffraction, refraction and interference. The photoelectric effect. In 1887, Heinrich Hertz observed that when light with sufficient frequency hits a metallic surface, it emits electrons. In 1902, Philipp Lenard discovered that the maximum possible energy of an ejected electron is related to the frequency of the light, not to its intensity. If the frequency is too low, no electrons are ejected regardless of the intensity. Strong beams of light toward the red end of the spectrum might produce no electrical potential at all, while weak beams of light toward the violet end of the spectrum would produce higher and higher voltages. The lowest frequency of light that can cause electrons to be emitted, called the threshold frequency, is different for different metals. This observation is at odds with classical electromagnetism, which predicts that the electron's energy should be proportional to the intensity of the radiation. So when physicists first discovered devices exhibiting the photoelectric effect, they initially expected that a higher intensity of light would produce a higher voltage from the photoelectric device. Einstein explained the effect by postulating that a beam of light is a stream of particles and that, if the beam is of frequency f, then each photon has an energy equal to hf. An electron is likely to be struck only by a single photon, which imparts at most an energy hf to the electron. Therefore, the intensity of the beam has no effect and only its frequency determines the maximum energy that can be imparted to the electron. To explain the threshold effect, Einstein argued that it takes a certain amount of energy, called the work function and denoted by phi, to remove an electron from the metal. This amount of energy is different for each metal. If the energy of the photon is less than the work function, then it does not carry sufficient energy to remove the electron from the metal. The threshold frequency, f0, is the frequency of a photon whose energy is equal to the work function. If f is greater than f0, the energy hf is enough to remove an electron. The ejected electron has a kinetic energy, Ek, which is, at most, equal to the photon's energy minus the energy needed to dislodge the electron from the metal. Einstein's description of light as being composed of particles extended Planck's notion of quantized energy, which is that a single photon of a given frequency, f, delivers an invariant amount of energy, hf. In other words, individual photons can deliver more or less energy, but only depending on the frequencies. In nature, single photons are rarely encountered. The Sun and emission sources available in the 19th century emit vast numbers of photons every second, and so the importance of the energy carried by each individual photon was not obvious. Einstein's idea that the energy contained in individual units of light depends on the frequency made it possible to explain experimental results that had hitherto seemed quite counterintuitive. However, although the photon is a particle, it was still being described as having the wave-like property of frequency. Once again, the particle account of light was being compromised. Consequences of the light being quantized. The relationship between the frequency of electromagnetic radiation and the energy of each individual photon is why ultraviolet light can cause sunburn, but visible or infrared light cannot. A photon of ultraviolet light will deliver a high amount of energy, enough to contribute to cellular damage such as occurs in a sunburn. A photon of infrared light will deliver a lower amount of energy, only enough to warm one's skin. So, an infrared lamp can warm a large surface, perhaps large enough to keep people comfortable in a cold room, but it cannot give anyone a sunburn. All photons of the same frequency have identical energy, and all photons of different frequencies have proportionally different energies. However, although the energy imparted by photons is invariant at any given frequency, the initial energy state of the electrons in a photoelectric device prior to absorption of light is not necessarily uniform. Anomalous results may occur in the case of individual electrons. For instance, an electron that was already excited above the equilibrium level of the photoelectric device might be ejected when it absorbed uncharacteristically low-frequency illumination. Statistically, however, the characteristic behavior of a photoelectric device will reflect the behavior of the vast majority of its electrons, which will be at their equilibrium level. This point is helpful in comprehending the distinction between the study of individual particles in quantum dynamics and the study of massed particles in classical physics. The quantization of matter. The Bohr model of the atom. By the dawn of the 20th century, evidence required a model of the atom with a diffuse cloud of negatively charged electrons surrounding a small, dense, positively charged nucleus. These properties suggested a model in which the electrons circle around the nucleus like planets orbiting a sun. However, it was also known that the atom in this model would be unstable. According to classical theory, orbiting electrons are undergoing centripetal acceleration, and should therefore give off electromagnetic radiation. The loss of energy also causing them to spiral toward the nucleus, colliding with it in a fraction of a second. A second, related, puzzle was the emission spectrum of atoms. When a gas is heated, it gives off light only at discrete frequencies. For example, the visible light given off by hydrogen consists of 4 different colors, as shown in the picture below. The intensity of the light at different frequencies is also different. By contrast, white light consists of a continuous emission across the whole range of visible frequencies. By the end of the 19th century, a simple rule known as Balmer's formula had been found which showed how the frequencies of the different lines were related to each other, though without explaining why this was, or making any prediction about the intensities. The formula also predicted some additional spectral lines in ultraviolet and infrared light which had not been observed at the time. These lines were later observed experimentally, raising confidence in the value of the formula. The mathematical formula describing hydrogen's emission spectrum. In 1885, the Swiss mathematician Johann Balmer discovered that each wavelength lambda in the visible spectrum of hydrogen is related to some integer n by the equation where b is a constant, which Balmer determined to be equal to 364.56 nanometers. In 1888, Johannes Rydberg generalized and greatly increased the explanatory utility of Balmer's formula. He predicted that lambda is related to two integers n and m according to what is now known as the Rydberg formula, where r is the Rydberg constant, equal to 0.0110 nanometers minus 1, and n must be greater than m. Rydberg's formula accounts for the four visible wavelengths of hydrogen by setting m equals 2 and n equals 3, 4, 5. It also predicts additional wavelengths in the emission spectrum. For m equals 1 and for n greater than 1, the emission spectrum should contain certain ultraviolet wavelengths, and for m equals 3 and n greater than 3, it should also contain certain infrared wavelengths. Experimental observation of these wavelengths came 2 decades later. In 1908, Louis Passion found some of the predicted infrared wavelengths, and in 1914 Theodore Lyman found some of the predicted ultraviolet wavelengths. Note that both Balmer and Rydberg's formulas involve integers. In modern terms, they imply that some property of the atom is quantized. Understanding exactly what this property was, and why it was quantized, was a major part in the development of quantum mechanics, as will be shown in the rest of this article. In 1913, Niels Bohr proposed a new model of the atom that included quantized electron orbits. Electrons still orbit the nucleus much as planets orbit around the Sun, but they are only permitted to inhabit certain orbits, not to orbit at any distance. When an atom emitted energy, the electron did not move in a continuous trajectory from one orbit around the nucleus to another, as might be expected classically. Instead, the electron would jump instantaneously from one orbit to another, giving off the emitted light in the form of a photon. The possible energies of photons given off by each element were determined by the differences in energy between the orbits, and so the emission spectrum for each element would contain a number of lines, starting from only one simple assumption about the rule that the orbits must obey. The Bohr model was able to relate the observed spectral lines in the emission spectrum of hydrogen to previously known constants. In Bohr's model, the electron simply wasn't allowed to emit an energy continuously and crash into the nucleus. Once it was in the closest permitted orbit, it was stable forever. Bohr's model didn't explain why the orbits should be quantized in that way, nor was it able to make accurate predictions for atoms with more than one electron, or to explain why some spectral lines are brighter than others. Although some of the fundamental assumptions of the Bohr model were soon found to be wrong, the key result that the discrete lines in emission spectra are due to some property of the electrons in atoms being quantized is correct. The way that the electrons actually behave is strikingly different from Bohr's atom, and from what we see in the world of our everyday experience. This modern quantum mechanical model of the atom is discussed below. A more detailed explanation of the Bohr model. Bohr theorized that the angular momentum, L, of an electron is quantized, where n is an integer and h is the Planck constant. Starting from this assumption, Coulomb's law and the equations of circular motion show that an electron with n units of angular momentum will orbit a proton at a distance r given by, where k is the Coulomb constant, m is the mass of an electron, and e is the charge on an electron. For simplicity, this is written as where a0, called the Bohr radius, is equal to 0.0529 nanometers. The Bohr radius is the radius of the smallest allowed orbit. The energy of the electron can also be calculated, and is given by. Thus Bohr's assumption that angular momentum is quantized means that an electron can only inhabit certain orbits around the nucleus, and that it can have only certain energies. A consequence of these constraints is that the electron will not crash into the nucleus. It cannot continuously emit an energy, and it cannot come closer to the nucleus than A0. An electron loses energy by jumping instantaneously from its original orbit to a lower orbit. The extra energy is emitted in the form of a photon. Conversely, an electron that absorbs a photon gains energy, hence it jumps to an orbit that is farther from the nucleus. Each photon from glowing atomic hydrogen is due to an electron moving from a higher orbit, with radius Rn, to a lower orbit, room. The energy gamma of this photon is the difference in the energies n and m of the electron. Since Planck's equation shows that the photon's energy is related to its wavelength by E gamma equals hc lambda, the wavelengths of light that can be emitted are given by this equation has the same form as the Rydberg formula, and predicts that the constant R should be given by therefore. The Bohr model of the atom can predict the emission spectrum of hydrogen in terms of fundamental constants. However, it was not able to make accurate predictions for multi-electron atoms, or to explain why some spectral lines are brighter than others.